In this video, we advance to page 8. On page 8, we're going to learn about the correlation coefficient and its significance when it comes to regression and correlation analysis. You see, the sample correlation coefficient is very useful for measuring the strength of the relationship between two numeric variables precisely, x and y. So, as we have seen in earlier videos, in order to describe the relationship between two numeric variables y and x, we start out with a scatter plot. So, to begin, it is no surprise that the first question we have here says that we should plot these variables in a scatter plot format. And based on this plot, what type of relationship appears to exist between the two variables? So this is what we'll do. We'll go to Start Crunch, and I'm going to look at my x and my y variable. And I'll go to Graph, go to Scatter Plot, and when I get in here in scatter plot, I'm going to select my x variable, which is going to be x. So right here, my y variable would be the y variable here, just for the sake of easy illustration. Then I would like to plot the line that would show me the general trend. So I will go to polynomial order. I want polynomial order of order 1. Leave it as the default best fit and click on compute. So here we have the line of best fit in this case. So what do we see from here? Well, let's go back to our notes. The scatter plot of y versus x shows a linear, reasonably strong positive association between the two variables with no apparent outliers. Please note, I talked about the form, I talked about the strength, I talked about the direction, and I also mentioned whether you have outliers or not. This should remind you of the details we discussed in the earlier video. The next step then is if we see, based on the picture here, based on the scatter plot here, that there is some relationship, we need to ask the next question, which is how strong is that relationship between y and x? To answer that question, we need the sample correlation coefficient. This is denoted by lowercase r, the letter lowercase r. So anytime I write lowercase r, I mean this is the sample correlation coefficient. Whenever it is well computed, its value will always lie between -1 and +1. What does that mean? Well, values of r between -1 and +1 definitely crosses the number 0. So it is possible that the r value could be 0. If r is equal to 0, it means that we do not have a linear relationship between x and y. I'll say that one more time. You see, r here only measures linear relationships. That is, when the form of the relationship is either positive or negative, linear relationships. But it does not measure the strength of relationship in curvilinear relationships. So when your r equals 0, it simply means that there is no positive or linear relationship between y and x. It does not mean that there is no curvilinear relationship. With that said, the closer the value of r is to either +1, the stronger the positive relationship. Or either way, the stronger r is to -1, the stronger the negative relationship. So how do we compute r? Well, there is a long winding formula for it, but you do not need that in this class. So in question B, to compute the correlation coefficient for this sample data and to indicate what the correlation coefficient measures, we can use Minitab, we can use StatCrunch. We are using StatCrunch at this point in time. So let's see how we do that in StatCrunch. I'll go back to StatCrunch and I'm going to minimize this. It's as simple as going to Stats, go to Summary Statistics, and you see that there's a special tool for it here called correlation. Click on correlation, choose X, hold down the control button to choose Y, and you can click on compute. And this tells us the correlation between X and Y is positive 0.954 to 3 decimal places. So in this case, let me take that back to our notes. That is where I got my R equals 0.954. Now we're going to embed this value. Oops. Let us take that back. 0.954. Take note that that value is very close to positive 1. So because it is very close to 1, this means that there is a very strong linear positive relationship between the values of x and the values of y. Again, note that R, this correlation only measures the strength of linear relationships. It does not work for non-linear relationships. Well, when we say something is strong, another key question we would like to answer in part C, which is where the bulk of the work is, it is to test if this relationship you observe between this sample x and y values is something that carries on into the general population of all x and y values. That is, testing for the significance of the correlation coefficient. So in this question, we want to test whether the population correlation coefficient is positive. And that is why in the alternative, I'm testing if this guy, the population correlation coefficient, which is written as rho, if it is a number greater than 0. So I want to check if it is positive. Remember, the alternative, the null hypothesis will be the opposite scenario then, which will be less than or equal to 0. This is synonymous or based on what we learned under hypothesis testing. So you want to be sure to state the null and alternative hypothesis, which is what we have done. The test hypothesis is the alternative where we want to test if the population correlation coefficient is positive. And so the null hypothesis will be the reverse, that it is not positive or equal to 0. And we would like to carry out this test at alpha equals 0.01 level of significance. So with that said, we would proceed to step 2, where we'll need to find the critical value and to state the decision rule using the t distribution with n minus 2 degrees of freedom. So how do we use the t distribution and how do we use the n minus 2 degrees of freedom? So step 1, you want to note that you need to find the degree of freedom first. That is giving us n minus 2. Our n in this case is the number of pairs of observations that we've been given in the data set. So if I go back to the data set and I count how many rows do I have here? 1, 2, as far as what? 10. So my n in this case, the sample size, is 10, which represents the number of rows of data. So 10 minus 2, that is 8. Set that down. Then we want to go and use the t distribution. And take note, this is a right tail test. So I'm going to sketch the t distribution and I'm going to locate the right tail. In the right tail, what is the size of this right tail? That is this alpha that was given, 0.01. But then what number cuts off that upper 1%? That is the critical value that we want to find using the t distribution. Well, StatCrunch comes to the rescue. Let's go back to StatCrunch. I'm going to close out on this. And I'm going to go to calculators. And I'll go to, on the stats, go to calculators, go to the t distribution. Let me drag this up here. And what you want to do is, what is the size of this area? That is your alpha, which is 0.01. So let's put that here. I'm going to put that in 0.01. What about the degree of freedom? It is going to ask you. That is your n minus 2. So n minus 2 is 10 minus 2, which is 8. So we're going to also plug that in, 8. And then what area, in what tail do you have this probability of 1%? It's in the greater than region. It is greater than an unknown value. So So I want to make sure I choose greater than. And immediately I choose greater than, it will tell me the proportion in the t distribution that is greater than an unknown value. And that unknown value is 2.8964. That is your critical value. Take that back to our working space. So 2.89646. That is the value right here. So set that down. Take note that you have the rejection region. So any value above 2.89646 for the test statistic will cause us to fall in the rejection region. So any value of the test statistic that is bigger than 2.89646 will fall in the rejection region, which will cause us to reject the null hypothesis. So at least we know the cutoff point between the rejection region and not the rejection region. So the decision rule then will be that if we get a test statistic value later in step 3 that is greater than 2.89646, the critical value, we're going to reject. It will fall in the rejection region. That is, the test statistic will fall in the rejection region. That will cause us to reject the null hypothesis. So let's check. So our decision rule, one more time, is that if the test statistic that will compute in step 3 later is greater than the critical value, that is, it falls to the right of the critical value in the rejection region, we will reject the null hypothesis. Otherwise, if it does not, we will not reject the null hypothesis. So step 3, let's go and find this test statistic we were mentioning here. The formula for the test statistic is the correlation coefficient you computed earlier, R, 0.954, divided by the square root of 1 minus R squared all over n minus 2. So I'm plugging in R equals 0.954 here, R equals 0.954 squared here. So let's make sure we write that clearly. There should be a squared there. So if you carry on all of this computation, you get 9.0002. This is your test statistic. Remember, the critical value was the threshold between the rejection region and the non-rejection region. This value, 9.002, is definitely greater than the critical value. So it lies to the right of the critical value in the rejection region. So it falls in the rejection region because 9.002 is greater than 2.89646. So that will cause us to reject the null hypothesis. If we are rejecting this guy, the null hypothesis, then the alternative is the winner. So this data provides sufficient evidence to tell us that the population correlation coefficient is also positive. So what we observed in this sample is statistically significant enough to carry on into the population itself. Okay, with that said, we proceed to page 9. On page 9, we are told that a bank's chief financial officer is interested in whether there is a relationship between account balances and the number of times a card is used each month. A random sample of 50 accounts was selected. The account balance and the number of charges during the past month were the two variables recorded. So take note, the two variables of interest, account balance, is a numeric variable, and the other numeric variable is the number of charges during the past month. And when the correlation coefficient was computed, like I showed you in StatCrunch, we are not given the data set this time. We were only given the reported correlation coefficient, which is reported to be negative 0.23. The question is to discuss what this correlation coefficient of negative 0.23 measures, and to make sure to frame your discussion in terms of the two variables, account balance and the number of charges during the past month that are mentioned in this context. You'll recall that your R value should always lie between negative 1 and positive 1. So you have 0 right here. I would argue that R equals negative 0.23 is closer to 0 than it is to negative 1. So this shows definitely a weak relationship. So A sample correlation coefficient of R equals negative 0.23 definitely measures the strength of relationship or association between two numerical variables, and in this example, it means there is a weak linear negative relationship between the two variables. So with that said, question B, we're to use alpha equals 0.1 level of significance to test whether there is a significant linear relationship between account balance and the number of card uses during the past month. We're to state the null and alternative hypothesis and to also show the decision rule. So how do we do that? Step one, to state the null and alternative. For the alternative, what do we want to test? We want to test if there is any relationship, any linear relationship. So in this case, unlike the last example, where we were told to test if it is positive, and we set population correlation coefficient in the alternative as greater than 0, that is positive, this time, please note, you are told to test if there is a significant linear relationship, which could be either negative, going towards -1, or positive, going towards +1. So this time, the appropriate alternative hypothesis would be that the correlation coefficient is not equal to 0, which means it could be negative or it could be positive. So the null hypothesis then will be left with just equal to 0. Our plan is to carry out this test at alpha equals 0.10 level of significance. Similar to what we did in the last example, we're going to find the critical value using the degrees of freedom and the alpha we have been given in the question. Take note, in this context, you have a both-tailed test or a two-tailed test. So I'm going to shade one tail here, shade another tail here. So what is my degree of freedom? I need n minus 2. Well, we were told that the random sample was 50 accounts. So it's going to be 50 minus 2, which is 48. And so I'm going to take that to my t-distribution calculator in StatCrunch. So here we go. I will go to StatCrunch. My degree of freedom this time is 48. And what next do I need? I do need, let's see, in particular, I can look at, I have two tails here. I can pick any one of the tails. Let me focus on just one. I can pick the greater than. So I want to find this unknown value, 1.672. So to do that, let me do this. I need to specify the size of this rejection region. Remember, since this is 0. This is what, 10%? 10% divided by 2. Why am I dividing it by 2? Remember, I have a two-tailed test. So 5% will be here, 5% will be here. So I need to specify 5% as being bigger than an unknown value, pretending that we don't know the critical value yet. So I'm going to put 0.05 for 5%, and I'm going to choose greater than and compute. So the unknown critical value is 1.6772. So that is where I got my 1.6772. A question I have gotten in the past is, could I have used the lesser than? Sure. Just specify that this is 5% and it's lesser than region. So let me show you that. So I could have also chosen lesser than. And did you observe? I still have the same number. So this is just saying 1.6772. And in which case, I just prefer to use the upper value because it's easier for you to relate with the picture. So if I put it back, 0.05, the 5% in the upper tail, since it's the upper tail, I'll change this to greater than or equal to same value. So now that we have the critical value, so take note, the lower value will be negative, the upper value will be positive. So what we would like to make clear is that these shaded regions are the rejection regions. So we're going to reject the null hypothesis if the test statistic we'll find in step 3 is either lesser than the negative 1.6772 or the positive, or is greater than the positive 1.6772. So we go on to step 3. Use the formula we have used before, r divided by the square root of 1 minus r squared all over n minus 2. Plug in the given value of r in the question. The correlation coefficient, negative 0.23. Plug that in, we get negative 1.677, 1.63, negative 1.6374. Negative 1.6374 is a number right here before negative 1.6772, which means our test statistic this time around does not fall in the rejection region. So since the test statistic does not fall in the rejection region, we will not reject the null hypothesis. So if we are not rejecting the null hypothesis, this is the winner here, which is saying that the correlation coefficient is not significantly different from 0. So, thus, we have insufficient evidence in favor of the alternative hypothesis. This means that based on this sample data, there is no evidence of a statistically significant linear relationship. So consider the decision you reached in part B. Describe the type of error you could have made in the context of this problem. Remember, type 1 error means when you reject the null hypothesis when in fact it is true, whereas type 2 error means failing to reject the null hypothesis when in fact it is false. In this case, take note that the decision we finally took was to not reject the null hypothesis. If we are not rejecting the null hypothesis, that is only connected with the definition of the type 2 error, which is when we fail to reject the null hypothesis when in fact it is what? False. So the only potential error that we can commit here by not rejecting the null hypothesis would be type 2 error, which is not rejecting the null hypothesis when in actual fact it might have been false. All right. So we look at another example on page 10. In this example, we are told that a concert promoter has randomly sampled 100 concert goers to determine whether there is a linear relationship between income level and the number of concerts attended per year. The correlation between these two variables was 0.68. So I'm going to note that. That is my sample correlation coefficient. And I've also noted that they randomly sampled 100 concert goers, so this is the sample size, lowercase n. Based on this calculation, is there a statistically significant correlation between income and number of concerts? Use an alpha level of 0.05. Step 1, as we have illustrated earlier, is to set up the hypothesis correctly. That is, look at what you want to test. Is there a statistically significant correlation? A statistically significant correlation will be either very close to +1 or very close to -1. So that means we are looking at a case where it is just significantly different from 0. That is, it is not equal to 0. That goes to the alternative hypothesis, which means we're going to have a two-tailed test. Okay, so that leaves the null hypothesis with the option of setting it equal to 0. Step 2, as we have done in the previous two examples, we need to get the degrees of freedom, which is n minus 1, and that will be 100 minus 2, which is 98, in order to find the critical value. Then I'm going to sketch my my t distribution, and it should have two tails. So one tail, two tail. The size, the combined size of both tail is my alpha. That is the combined size. So that means 2, if this is 5%, 2.5% will go here, same as 0.025, and 2.5% will go here, 0.025. And so with that said, I can proceed to my T calculator. So I'm going to go to my T calculator, and I'm going to specify degree of freedom, 98. Back to the question, 98 is my degree of freedom. And in the upper tail, I have 0.025. That is 2.5%. So let's go back here. I'm going to choose 0.025. And I'm going to choose greater than compute. And so this is the critical value, 1.98445. So let's go back. So 1.9845. That is the critical value in the positive realm, and in the negative realm, since this is a two-tailed test, it will just be the negative value of this right here. So I'm ready to write my decision rule. I'm going to reject the null hypothesis if the test statistic is going to fall in the upper tail, that is greater than 1.9845 or lesser than negative 1.9845. So let me go and find that test statistic so that I can put an end to this. The test statistic is r all over the square root of 1 minus r squared divided by n minus 2. So what is my r? I was given my r earlier, the sample correlation coefficient, 0.68. I'm going to plug r equals 0.68, 0.68, and n, which is 100 here. You should get 9.1810. And I'm going to make a decision. How do I make a decision? To reject or not to reject the null hypothesis. Where does 9.1810 fall? It falls in the area above 1.9845 on the number line because it is bigger. So since the value of the test statistic is greater than 1.9845, it definitely falls in the rejection region. Anytime the test statistic value falls in the rejection region, this means you should reject the null hypothesis. Thus, we conclude at alpha equals 0.05 level of significance or 95% confidence level that there is sufficient evidence in favor of the alternative since we are rejecting the null hypothesis. And so, and if we have evidence in favor of this, that means there's a statistically significant correlation between X and Y values. What are the X and Y values here? Between income and the number of concerts attended per year. All right, with that said, let's go on to another example on page 11. On page 11, we're told that a regional retailer would like to determine if the variation in average monthly store sales can in part be explained by the size of the store measured in square feet. A random sample of 21 stores was selected, and the store size and the average monthly sales were computed. Here's the data set as an example. The results are shown here. And so we want to look at that data set and construct a scatter plot using this data. The first step is to know who is going to play the role of X and who's going to play the role of Y so that we can assign them appropriately in the scatter plot. So what do you think? Do you think store size would depend on monthly sales? Or do you think that monthly sales probably would depend on store size? I would, in my own thought process, think that monthly sales, average monthly sales, would depend on the store size. So this is your dependent variable Y, and store size will be our independent variable X. So let's go into StatCrunch, and I'm going to X out of this. So I have store size and average month. And what is our first question that we'd like to answer here? We'd like to get what? The scatter plot. So let's go. We'd like to get the scatter plot and possibly the sample correlation coefficient R. So let me do that. Let's go to this. And I'm going to start with graph, a scatter plot. My X variable will be the store size. That is this variable right here. And my Y variable would be average monthly sales. And I would like to overlay a polynomial of degree 1. Leave this as is. We want to find the best line that captures the trend between store size and average sales. So click on compute. And here we have, voila. We have the scatter plot, and I can see definitely a linear trend. The form is definitely a linear. The direction is positive. I can see that, I don't know, do you want to classify this as what? An outlier or not? Maybe, maybe not. Okay, and so from the scatter plot obtained using technology, there appears to be a moderately strong linear positive association between store size and the average monthly sales. Next, we would like to get the sample correlation coefficient between size and average monthly sales. So let's do that. So we go back to StatCrunch, X this out, go to statistics, summary stats, and we would like to summarize the relationship between X and Y using correlation to measure the strength of the relationship. So correlation, click on store size, hold down the control button to choose the other one, and um, we can also choose a two-sided p-value if we want. And so click on what? Compute. So in this case, you have the correlation between store size and average monthly sales is 0.8514, and the p-value is very, very small. In fact, it is smaller than 0.0001. So here we have that. We have that report value. I mean, the reported values here. R equals 0.851 with an associated value of literally 0 because it's very, very small. Then we have to conduct a hypothesis test to test if a positive correlation exists between store size and average monthly sales. We have to use a level of significance of 0.025. Since we want to determine if we have, in this case, a positive correlation, that would send to that information will send to the alternative, which is this time testing strictly if it is greater than 0 at alpha equals 0.25 level of significance. So the null hypothesis will take the rest, which is rho, or the population correlation coefficient, less than or equal to 0. Then, as we have established earlier, we're going to find in step 2 the critical value using the degrees of freedom. So step 1 will be to draw or sketch the t distribution, which we have here. And so when I sketch it, how many tails should it have? Well, this is a right one-tail test. So you see that tail right here. And what is the size of this tail? That is your alpha, which is 0.025. It is just by itself, so there's no need to split this one. This is just a one-tailed test, all concentrated on the right side. And we need to find the critical value. So how are we going to find this number? We're going to need the degree of freedom, which is n minus 2. What is our n? Our n in this case is how many values do we have? How many pairs of values do we have? A random sample of 21 stores was selected. So there were 21 rows here. So take that here, 21 minus 2, that gives you 19. So we're going to go into StatCrunch, and I'm going to close out of this. And I would like to go to my calculators, go to the t distribution calculator. I'm going to drag this up here. For the degree of freedom, that will be 19. Where did I get that from? Just to remind you, 21 minus 2, that is 19. And then my alpha is 0.025. So I'm going to key that here, 0.025. And this area, 0.025, is located in the upper right-hand corner of what value? Of 2.0930241. So here it is. So 2.0930241. So at this point, any value of the test statistic that is greater than this critical value will fall in the rejection region. So I can write my decision rule. I'm going to reject the null hypothesis. So if the test statistic we're going to compute in step 3, if it falls, if it is greater than this value, 2.093. So let's go on to step 3, where we're going to compute the test statistic. Plug in the value of R, which was 0.851 that we got, and we get 7.0633. So the test statistic in this case, 7.0633, where does it fall on this number line? It is a number greater than 2.909. So it definitely falls in the rejection region. So since the test statistic falls in the rejection region, we're definitely going to reject the null hypothesis and say that there's a statistically significant evidence that a positive correlation exists between store size and average monthly sales. If you're going to use the p-value method, you'd note that the p-value here, which is 0.000, is lesser than less than our alpha. Anytime the p-value is lesser than alpha, we always reject the null hypothesis, which is consistent with what the test statistic 7.0660633 greater than 2.09 and falling in the rejection region, what it led us to conclude. So whether you use test statistic, which is 7.0633 versus the critical value, or you use the principle of p-value lesser than alpha, lesser than 0.025, we still end up with this correct decision here. And that is, these two observations lead us to reject the null hypothesis. So we're rejecting this guy, and we're concluding on the alternative that there is a positive correlation between store size and average monthly sales.